Okay, let's start. Good morning, everybody. I'm Federico del Prete from Politecnico di Milano. Today, this is a workshop of our final event. Our means SATO project, but this workshop hosts also another H2020 project, which is SMART2B. And we chose as title Energy Demand Flexibility for a Faster Energy Transition. And let's start with a number, which is a well-known data, actually. 36% of greenhouse gas emissions in the EU are come from the existing building stock. And probably more is coming from the new one. Maybe not everywhere, but at least somewhere, we should be worried about a further greenhouse gas emission caused by the existing building stock. This should make us even more conscious about our role in the energy transition, which each of us hopes will be as fast as possible. And this is why we decided to name this workshop as such. Reducing energy demand of buildings. It's the theme of today's workshop, and focus is on the building envelope because deep thermal insulation of walls, fixtures, roofs with new methodologies and techniques bring us to the point of almost completely eliminate thermal breaches. These techniques not only give a more stable and value application to IT platforms for the energy demand assessment, such as the SATO's one or the SMART2B ones, but expands the time interval in which the indoor temperature remains comfortable even in the absence of heating or cooling. And this is, of course, the building as a battery logic. This kind of flexibility makes a faster energy transition towards renewable sources possible, also reducing energy demand altogether, and we are talking about up to 80%. So it's going to be a huge. And Smart Readiness Indicator, which was introduced by EPBD directive, finds a greater effectiveness in deep thermal retrofit buildings. This workshop would update the various advantages of a properly designed deep thermal envelope with the presence of discussants ranging from the academia to the industry, and themes that focus on construction site costs to user interface. In short, we will have an overview of the two H2020 projects that contributes to these methodologies. But first, let's have a short overview about our 7 discussants from 5 institutions. We have Politecnico di Milano, we have the Faculty of Science of the University of Lisbon, we have the City of Milan, and EDP New, and KNAUF. Let's start with SATO project coordinator, Professor Pedro Ferreira, for a short overview of the SATO project. You were what?
Was it in the schedule?
Yes. But you can also, yes, it was in the, okay, but no problem. You can just do it like explain shortly. And also is preparing Joao with a short introduction about SMART2B before beginning with the presentations.
Okay, I will be very brief. So, is this working?
I don't know. Maybe you should just turn it on.
Yes. Hello?
Okay.
Yes, now it's okay. Okay, a brief introduction to the SATO platform. This project was responding to a call, an H2020 call, where the challenge was to, let's say, decrease the gap between building energy performance on design, and then decreasing the gap to the real energy consumption that can be measured and that actually results from the utilization of the building. And by reducing this gap and providing the right tools to the managers, owners, occupants, depending on the role of each of these actors in the system, we should provide information, assessments. The word assessment is the strongest word, I think, in this project, since SATO stands for self-assessment towards optimization of building energy. And to respond to this challenge of providing informative assessments to the right stakeholders and the right actors in the system led us to design and propose the development of a platform that was structured in 4 layers, from the middleware that is data and systems integration middleware, and also an orchestration middleware that can arrange and execute all the processes necessary to assess and optimize the energy. Then there is a second layer that uses all the data already harmonized that comes from the different systems in the buildings, which is the self-assessment framework. It's the main, I would say, the main topic of development in the project. It's a library of assessments that can provide information about the performance of the building envelope, the building systems, the occupancy of the building, so different aspects that have an impact on the energy efficiency of the building. So on top of this, let's say, knowledge layer, we have the energy management services that can do either aggregated control, actually controlling systems in the building, or having advisory services that provide information and advisory on how to proceed in the management of the building. And finally, we have a set of interfaces with the different users using web-based technologies, mobile applications, and beam-based interfaces that we use to display in 3D models based on the beam model of the building. We use these interfaces to easily convey information about the assessments that we made on the zones, the rooms, or the whole building. And that was the main idea of the SATO project. So I think today in the workshop, as Federico was introducing, I think the workshop will be geared towards the envelope and the flexibility possibilities that are present in the buildings, also letting you know of some of the assessments and how they contribute to the self-assessment framework that I was introducing.
Thank you, Pedro. Joao, just a few words about SMART2B.
I have a short presentation.
Okay, please, yeah.
Maybe you can.
Yep. Short.
Yeah, I'll do it very briefly and just to complement the information that was. Maybe I should.
No, you can use this one. Oh, you're standing.
Yeah.
Okay.
So
that's the clicker.
Is it on? On, yeah.
Okay.
Okay, yeah, it's working. Perfect. Good morning. So my name is João Martins. I work at EDU, and this is not on.
You should put it on.
Maybe not, but yeah. Sorry. So my name is João Bravo Dias. I work at EDP New, and as Pedro said, and our objective here is to present the Smart2B project. It was a project that started 3 years ago and ended last month. We are now, Smart2B is very, very similar to the SATO project. We have also some partners that are common between both projects. It was a 3-year project, 4 million euros, 11 partners from 8 different countries, and with 5 pilots that I will briefly explain later. So the concept of Smart2B is very similar to the one of SATO, but we have different terminology, so we don't have assessments, we call it services. And the basis was more or less the same. We have 3 different layers. We have the Smart2B devices that were developed or upgraded during the project. Then we have the Smart2B platform, and then we have the services. The objective here is to make buildings smarter and make them also active on the energy grid and active with the citizens that interact with these systems. Basically, we have 3 different impact layers. The first one and the most important because it will result in the impact on the other ones is the technical ones. And the objective here is to increase the energy efficiency and tap and flexibility potential that was previously untapped, and also upgrade the smartness of the building. And then we have the environmental impacts, for example, reducing CO2, increasing the primary energy savings, and also the social impact that comes up with this concept. Smart2B has 4 different technology pillars. The first one are the devices in building interfaces. So we have developed or upgrading during the project devices that are installed in people's houses that can enable the monitoring of energy consumption and also production, but also enable the control of some of devices. We have, for example, the AC plugs that can measure energy consumption, but also can send infrared signals to the AC devices that we have in our house, and does controlling these devices. But we also have switches that can control heat pumps or other types of appliances that can be switched in and switched out, on and off, sorry. And we also used some indoor air quality sensors that actually were developed by Excel, which is a partner of SATO, but we also use them in this project. Regarding non-residential buildings, the concept is more or less the same, so measuring and controlling. We also have devices that were developed by EnerBrain, which is a partner of the project, both on the level of indoor air quality, but also on the level of energy monitoring and control. The second layer is the platform and the APIs. Basically, here the objective is to make the bridge between the measurements and the services that will be calculated afterwards, but also between the results of these services and the actual control of things inside the building. Then we have the management and transversal services, so this is the most interesting part for the discussion today. I will come back to this later, but very, very shortly, because it's a confusing slide, I know. On the top, we have the Smart Readiness Indicator methodology, and here the objective of the service that were developed was to align them with the Smart Readiness Indicator and the methodology that was developed. And then in Smart2B, we developed services in 2 different ways. The first one is the multi-criteria and multi-asset level, so the most important services that were developed. The last 3 that we have here, so the local energy efficiency, flexibility services, indoor air quality, they work by themselves. And then the first one, the multi-criteria, basically aggregates the concept of them all, and according to the specification and the optimization that was developed, will result in the best option for the development of these services. Then on the bottom part, we have transversal services that basically complement the ones that were developed before. I will come back to this later. The last pillar is the user interaction, client engagement, social innovation. Basically, there was a user interface that was developed. This is the actual demonstration of it. Basically, you can see how is the energy consumption, production, the comfort inside the different rooms. We also have the possibilities to see how is the comfort by the votes of the occupants, but also by the people that live in there. We also have the possibility to check what's the consumption with different layouts and different views. So you can go on a weekly basis, daily basis, hourly basis, but also focusing on the different types of services that were developed. We also can compare the consumption of these buildings and the other services to the typical building or similar buildings that exist with the same configuration. So we can see if the consumption are higher or lower than usual. And it also applies for the production and the other variables that we have there. Finally, we also have this possibility to vote. So if we are cold, fresh, warm, fresh, I think it's more or less similar to something that SATO also has. So basically, this is it. The last module is the gamification component. So people can, we also have this possibility to gamify the experience of energy engagement. This is especially interesting for younger kids that we have in one of our pilots. Here, there's monthly missions, weekly missions. There are some games that people can play, questionnaires to respond, and the experience of them will increase during the project.
Okay.
Finally, this is the pilots. The first one is the Lisbon Airbnb, which is a mix between a residential building and a hotel, so it's not exactly one of them, but consumption is not typical from residential, but it's also not exactly as an hotel. This is an interesting case. Then we have Lisbon Social Community that are 9 buildings and 13 apartments that are for foster kids. So their energy consumption is quite stable and compared to more or less residential houses. Then we have Aalborg Residential District that uses a retirement home and 20 apartments. Then we have a shopping mall in Sweden and an office building in the southern part of Spain. Just to finish, some lessons learned from the project on these last 3 years. Basically, not all IoT services and building energy systems are enabled by an open source, so it's a bit complicated to integrate in the platform. We are trying to do that, also combining these with the SMART2B, with the Google Assistants or the Alexa, for example. It's also hard to convince building owners to allow us to monitor and also control, and especially control some of their appliances and uses. There's a lot of incompatible expectation between building users, the project consortium, and also, most important, the Energy Commission. Finally, there is the one thing that we thought worked quite well was the user-in-the-loop services that reveals big potential to reduce the intrusiveness and the fact that we don't have to enter in people's house and control directly their appliances. And finally, one very valuable tool is the user-centric design that allow us to come up with better ideas and be more straight to the point what users need. Thank you.
Excellent. Thank you very much, Joao. And now is the turn of Professor Pagliano from Politecnico di Milano, which I'm going to help with this presentation. The title is very, complex. It's a whole world of things, but this will get us deep into the flexibility matter. Please.
Okay, hi to everyone. Flexibility through the envelope. And so I will start with looking back at the Smart Readiness Indicator. Does it involve clearly this issue of the envelope? Flexibility obviously is my big topic, coming by train and bike in spite of a number of family issues last week. So I be flexible. And okay, but apart from personal flexibility, Dunque, to go on, okay. Yeah, so I just recall the fact that some elements that I will show are obviously in the smart readiness regulation. Energy flexibility, but also response to the needs of the occupants. Quality of the space is part of it. And there are a range of technical domains that the regulation lists, and also national governments might prepare catalogs of services pre-evaluated. So that might be of interest for us. Obviously the formula and, okay, I have to advance on that computer, not on mine. We will not go, anyway, it's a weighted average over a number of services. Each of them has a score, and the final score is the weighted average of the individual elements that are analyzed. So as it has been shown, then each of those elements is evaluated using, sorry, I need some water. Water, which I had prepared in advance, but
Here you go.
here I go. Thanks. By the way, I'm taking some pictures that are from a report of Vito, I think a technical report commissioned by the Commission. So credits for I think the drawings are from them, I guess. So there are various ways of analyzing those elements. Criteria, one criteria is fault prediction, which obviously is one of the objectives of SATO. Comfort, information to occupants, again, that's one of the things that SATO and SMART2B are addressing. And flexibility offered to the grid by the building, and storage offered by the building. And then each criteria is weighted with respect to a maximum possible value of that particular criteria. So as I was saying, there is not only flexibility, there is energy efficiency, so how much energy is used, comfort, and well-being of the occupants. Many other criteria, but let's see the ones that are more relevant. And the technical domains that are evaluated, so the end users are a list of heating, cooling, domestic hot water, ventilation, lighting, dynamic building envelope. So the envelope is cited only for the dynamic elements like opening window, open or operable windows, operable solar protections, for example. While we know that flexibility is offered also by static elements, the mass of the building, the insulation, the geometry of the building. So this obviously might come in, and hopefully will come in the national implementations to cover also this important element. And then at the end of all this process of looking at the various end users, evaluating each of them with the criteria, there is a sum of over all the end users, a weighted sum, and each of the criteria is compared to a maximum value possible. So you have a score which goes from 0 to 100% for each element, and the sum goes from 0 to 100%. And so you have proposed categories depending on how close you are to the maximum. And the evaluation could be simplified, made by an assessment, let's say by a person, helped by tools like the ones we are discussing in the projects. and based, for example, possibly on measured data also. And finally, the regulation foresee that national governments might simplify the work by pre-cooking some of the elements and delivering a catalog of elements which are relevant for the smart readiness. And again, it's probably an area where it would be important to act. So to go to something concrete that we can offer from the SATO project, the case study in Italy is this building owned by the city of Milano and retrofitted by the city of Milano to very low energy needs. So in fact, it has become comparable to a passive house, and we will have a specific presentation on how this has been done by the colleague Andrea Sangalli. And within that, we have two apartments which are laboratories, so where we perform measurements. We have a set of instruments. We have the possibility to condition those apartments separately from the others with cycles that we decide. And if we go to simulations about those, after the retrofit, let's imagine that for 1 day, that's the black curve, we heat the building at the higher level of comfort, 24 degrees, for 1 day, and then we let it go without any energy input under specified conditions, which are shown here. So under an average winter day where we have 0 degrees at night and a reasonably good irradiation. If I go back, what we see is that operative temperature, which is what determines comfort, so an average of air and surface temperatures in the room, yes, it decreases, it oscillates due to input from internal heat gains and solar heat gains mainly. And the point is that it takes 1, 2, 3, more than 3 days to go out of comfort, so below the lower threshold of comfort. If we, in fact it's 4 days, okay. If we keep the heating on for 2 days, then we have the red curve, and the simulation show that we are in comfort for 5 days without energy input at all. And so on if we have a charge phase of 3 days and so on. So what shows the simulation is that with 1 or 2 days of charging the building, then we get this autonomy, comfort autonomy of 3 to 4, 5 days. We don't need to charge for 5 days. We have already saturated the thermal capacity of the building in a couple of days. Okay, and that's obviously our simulations. So may we trust them or not, that will come. Okay, here, again, simulations of that building, that specific building. Before the retrofit, you see the black line. Comfort drops very quickly in 1 day. If we add let's see. Okay, yeah. This line is if we change the windows with high performance windows, we get some flexibility, but not much. Then we add external thermal insulation. In this case, it has been 25 centimeters of external insulation and removal of the thermal bridges. We get, again, we extend the thermal comfort autonomy to 1, 2, 3, 4, 5 days. If we add additionally heat recovery on ventilation, we go even farther. So that's, again, just simulations with Energy Plus, so we can trust or be skeptical. Let's go to measurements in that building, in the apartments that we are testing. We are testing with a number of, we are measuring a number of parameters. We have global thermometers, temperature resistance thermometers, and so on. And then also CO2, relative humidity across the apartment. And what we get is measured data with the real weather. Here is the temperature goes below zero in many nights. And we get for the retrofitted building this curve. It starts here, we charged only at 21, we didn't go to 24 for 2 days. And this is how the evolution. So it gets to 19 and it stays to 19 for 5 days. A non-retrofitted building of the same type goes to 15 degrees in a few days. So we are going down to what is considered a non-safe level of temperature for, at least for fragile people. So the difference between the two buildings is clear, measured. So you can imagine pre-retrofit, after the retrofit. And obviously the flexibility offered by the two buildings is completely different. So more detail on the measurements. We have another experiment done in the lab, which is under responsibility of Sangalli. So we have charging at 22, 23 degrees for, I guess, a couple of days, maybe more, 3 days. And then we let it go. No eating. And so the temperature drops, and you see it drops not even to 20 after a few days. Okay, measured in different ways with a global thermometer or with surface temperatures and view factors. So 2 ways to calculate the operative temperature. And obviously we see when there is solar irradiation, we have some solar gains that bring up the temperature and help the building to perform passively in comfort. I guess I can go on like this. So, but that's the apartment we are testing, which is this one, where we have more detailed measurement, but we have also measurement, as in many SATO buildings, across the entire building. So we have measurement of air temperature, relative humidity, and CO2 in all the apartments. And obviously, running the experiment there and saying, okay, you don't have heating for 1 week would be a bit strange for the occupants, but it happened. The heat pump just went into stall, idle, for 1 week, and that's what happened. The apartments who started well in comfort at 22, 20, during the 2 interruptions, so the white part is when there is no energy coming to the building. Yeah, there is a decrease in temperature, but we see that we go to, again, 19 degrees for those who started at 22, and below 18 for those who started already below 20. So we lose 2 degrees over a week of no heating in the entire building. And in fact, we discovered that it was not heated, not because of complaints from the people, but by chance. So there are other effects. So if we look at the operative temperature, in Italy, we turn off by low the heating at night. So you turn off the heating, and obviously the temperature goes down, but obviously there is a difference. Pre-retrofit, you go down to 17 in average, and after the retrofit, you go down just to 19. Then obviously, in the morning, you have to bring back the building to comfort. And in terms of required power, obviously, the pre-retrofit requires, I don't know, 120 kilowatt in the first 2 hours of the morning to be brought relatively rapidly to comfort. After retrofit, we need 30 kilowatt thermal. And you can imagine what that means if you're using a heat pump. The difference on the electric demand is factor 4. But there is also an effect on comfort, because pre-retrofit, yes, in average we go down to 17, but some apartments go to 15 in one night because they are, and that was what people were complaining before the retrofit. So there is a huge difference between one apartment and another, depending on where the apartment is within the building. After the retrofit, you are in a very insulated envelope, and all the apartments behave more or less the same. So comfort, another of the parameters that the Smart Readiness Indicator requires is comfort, well-being, and so on. And we are improving that. We are not improving only flexibility for the grid, we are improving comfort for the occupants. And we have no more molds or other things that unfortunately were present before.
Okay, thank you, Lorenzo. And maybe you forgot to say that those buildings are of social housing, and it's of course property of the city of Milan, which will report after the first break. About all the influences this H2020 project caused to their maintenance of their building stock, which is really inspiring, I guess, for a lot of other contexts. Now I leave ground to Joao from ADP. Guilherme. No. SID. Okay. It's a mixed, program this morning. Okay.
Do you have the pointer?
Yes. We should launch your presentation, right? Okay. Which is yours?
If you give just 1 second more. The credits are important. So the buildings are buildings of Comune Milano, social housing, and the
maybe is this one?
technical department of the city has worked hard. They are not present today, but maybe Fabrizio and Silvia, and okay, will be quoted later. Okay, that's and interaction with industry has been important in doing the retrofit and finding the right products, having support for the simulations, and Knauf Insulation Italy has been an industrial partner for working on this issue of flexibility in Italy. Just to mention everyone who has contributed. Okay, and now, so I fill the void in the meantime.
Hello everyone, my name is João Simões. I'm a PhD student at FCID, and I will talk about thermal inertia-based building electrical demand flexibility and our approach using an RC model and how we developed and calibrate these models in order to deploy it in flexibility. So just to give you a little bit of introduction and context, with the European Union goals, there will be an increase of renewable energy sources in the generation mix, and with that, with the nature the intermittent nature and controllable nature of these generation sources, it will induce a lot of power imbalance between demand and supply. Additionally, with this increase in renewable energy sources, also in the demand side, there will be, we will move toward, from a centralized energy system towards a decentralized energy system, creating a lot of reverse power flows and voltage violation, congestion problems, and with that, we will need a lot of flexibility in both sides. Another point that it's in favor of demand flexibility is the increasing number of controllable and flexibility units like heat pumps. And in most of the buildings there is a lot of thermal inertia capacity that can be a cost-effective solution to substitute conventional batteries. So, what is the thermal inertia flexibility? Our approach is try to turn off the HVAC and measure and assess how the duration that we can turn off the HVAC and the flexibility that it allows. So in the first figure you see like a profile load of a building, and then you have a close-up of how this is quantified. So you have the duration, DHO here, which is the duration of HVAC of time, APR, which is the average power reduction from the HVAC, and TEF, as we call it, which is the thermal electrical flexibility, that is like the multiplication, the APR to DHO. So the challenge is to implement and test a cost-effective solution, and with that we came across with the concept of soft sensor. The concept of soft sensors is we integrate multiple measurements from different sensors, and with some piece of software we combine these different sensors to allow a new measurement possibilities. This concept of a soft sensor, or also it is also called virtual sensors. It is a lot of it is used like in the chemical field and a lot of other fields, and we are trying to apply it in buildings. So our soft sensor starts by, we have the measurements of indoor air temperature, the thermal energy that is being put by the HVAC, and the power that is being measured by the meter that we have. And with that, we used an RC model to calibrate the parameters of the RC model with that measurement, and then we assess the potential of the flexibility that we have in each moment during a day. So, as I was saying in the previous slide, the thermal inertia flexibility is the average power reduction multiplied by the duration that we can turn off the HVAC. This is our model that we are using, 2R to C, where this C, it misses an F, which represents the light inertia and light elements of the building. Cm represents the long-term heat capacity of the thermal mass. Rho is the indoor-outdoor thermal resistance, and Rm is the air-to-surface convection coefficient. These are composed by two differential equations. One that, as I already mentioned, is related to the light inertia that Cz in this case is the capacity of the zone, and it has like these two parameters, as I explained, and the second differential equation is related to the mass. So how we will calibrate? We have these 4 parameters that we don't know. We use the measurements that we have, and with an optimization model. And in this case, I use the particle swarm optimization to find the parameters that represent that measurement. And with that, we calibrate our model. This calibration can be done if you know the internal gains, like if you have an occupancy sensor in the zones and you know exactly which are the convective heat gains that you have in the zone, or another approach that we have is like you preheat the zone without anyone, so you have controllable heat gains. You know exactly what is the thermal energy that is being put in the zone, and with that approach, it's more safely and more accurate, you know, because estimations of convective heat gains from people is quite difficult. So probably this is the best approach to do it without interfering with occupant comfort. And after that, since this approach will use the building in its operation, the threshold of flexibility is the occupant comfort. For that, we use the drift durations that ASHRAE recommends to assess the potential of flexibility that we have in each time. These are the categories. We will focus on category 1 and category 2 mainly because most of the buildings will only be able to do at least the first 3. The last 2 are very ambitious, at least. So we start by, after we develop the concept, we start by validate our soft sensor in 2 different test cells that we have. These test cells were really good to test if our soft sensor is good to capture different thermal inertia, different thermal inertia within zones. So we have 2 test cells, one with very light inertia with a lot of insulation inside, and the other one is a very heavy, mostly concrete. And what we conclude is that the model can capture different capacitance within the zones. And after seeing the parameters that we achieve with that calibration, we just validate if we can predict well the indoor temperature with our model. So in the first column, so this is the first row is related to the light thermal inertia test cell. The second row is related to the heavy thermal inertia test cell. And in the first column, you have the fitting process where we fit our model. And the second and third row is like the operation of the soft sensor with different scenarios. F is related to the furniture. We put it like 12.5 kilograms per square meter of furniture, and the G is related to the internal gains, 60 watt per square meter of internal gains, and with different scenarios we have a good prediction of the indoor temperature. After validating our soft sensor, we start deploying this approach in SATO pilots. One of the SATO pilots is Seychelles office building. This is a very big building, and we just focus on one zone, the open space office, in order to assess. Because despite this building is very big, in the SATO, just 2 of these zones are in SATO, which is the open space office and the main atrium that represents the SATO pilot. And when we deployed, we calculate the duration for different scenarios, like 25 watt per square meter, 50 watt per square meter, and 75 watt per square meter. These numbers include like internal heat gains and solar gains. We have done a review of internal gains, typical internal gains in office buildings, and we came across with the usual number is between 25 and 50 watt per square meter. This is like the worst scenario that you can have in a zone, and we assessed that for different outdoor air temperature, and we can see that mainly the green color the green colors means that it respects the threshold that the ASHRAE have. The yellow one is where it's very close to the threshold that ASHRAE has, and the red ones are very far away, and these scenarios where we cannot deploy this soft sensor. Conclusions is that the thermal inertial flexibility is around 5 and 12 watt-hour per square meter for a 1.1 degree increase in indoor temperature, and the minimum duration is 9 minutes, but if you consider the typical is more than 15 minutes, which is very good, especially for balancing markets, for example. So one of the possible applications is you can deploy this in implicit demand response and explicit demand response. This is just to implicit demand response is like the typical markets, like they had markets, intraday, real-time markets, where explicit demand response, where you have like an event, a specific event for deploy the flexibility. And this is just an example of deploying that other power grids, grid operators have been deploying like demand-side assets to balancing the market, basically. What is our step? Since this approach is a zone-by-zone approach, we will need to aggregate different zones in order to have a product to the grid. So here we have different zones. Let's call it each zone an asset. And in this figure, you can see that the light blue is the maximum available flexibility that we have, and the dark blue is the deployment of the asset. So you can see that each moment, not all of the zones will be deployed, and it depends on the requirements that the grid has. And this is the next steps where we will aggregate depending on the needs that the grid has. And that's it.
Thank you very much. And so in this flexible program, I guess the next one is you, Joao, right? So there are two Joaos, and I just inverted the two. Thank you very much. Yes.
So I'm back and continuing with Smart2B and the services that we developed during the project and some of the results that we achieved. So I mentioned before the service layer. I will now explain a bit better what all of these arrows and boxes mean. Just an overview again. On the top, we have the Smart Readiness Indicator, the methodology, and the typical domains that exist. And on the bottom part are the services that were developed in Smart2B. On all these services are related with the methodology of Smart Readiness Indicator, and we also have this service layer that are complementary to this one. This means that these transversal services will feed the information on the multi-criteria, multi-asset services, and these last three will feed the multi-criteria load scheduling services. It's a bit complicated, but basically we have three different services that are important. So the first one is the energy efficiency, so to reduce and increase the energy efficiency inside, the reduce consumption, increase the energy efficiency inside the buildings. We have the flexibility services that will allow the use of the potential that exists inside residential and commercial buildings, and then use this to also reduce energy in general, and general consumption in general, and energy prices. And then we have the indoor comfort service that basically takes in consideration the comfort inside the rooms and make sure that people are not freezing because there's a lot of flexibility inside it. A bit on the multi-criteria load scheduling. Basically, it considers the efficiency, the flexibility, and the comfort services, and considering all that was developed before, and also the user preferences that were defined by the users and also assessed by the platform through the data that existed before, it will come up with a prediction of what will be the best actions to be done by the users or the platform inside homes. It considers the consumption optimized baselines, the flexibility tokens offers or energy flexibility zone, the prediction of renewable energy generation that exists, and also the price tariff that exists, for example, with the day ahead, in the day ahead markets. Aggregating all of these through MDP methodology, we get a general reward function that basically will tell us what to do. Minimize energy balancing and minimize costs will be the primary objectives in the end. Regarding the indoor comfort service, we also used an RC model similar to the one João Simões just presented before. And basically here what we wanted to do was kind of similar, trying to understand what's happening inside the building, predict what will be the thermal mass behavior according to the user occupancy and also the thermal loads that we have inside. And based on that, we're going to have a prediction what will be the comfort zones or the limits up and down that the building can handle during its operation. Then we have the local energy efficient servicing. Basically here, the object will be to increase the energy efficiency of this, of the building. It will consider forecasts, for example, on weather, occupancy, building mass that exists on the storage, and also based on all of these criteria with the model predictive control, we're going to have a perspective what will be the reduction and how the energy efficiency will increase with the actions that users can take. Moving to the flexibility services, and I think this is the main reason we are here. The flexibility, we consider a three-stepped approach. So on the first hand, we have the flexibility aggregation. And on that part, we're going to consider everything that is happening inside, all the equipment that exists inside the building and their flexibility. For example, if you are in a residential house, we can consider the HVAC, EV chargers if they exist, but also the appliance that can be controlled by us or controlled by the users in their house by receiving set points. After making this calculation, we ran a cost optimization function that basically collects the information of the energy consumption profile, considering what also is the typical use of that household or that commercial building during the similar days. And based on that, we have a load scheduling services that feeds these, and we can predict what's going to happen. Afterwards, after all the calculation of this flexibility potential and also the cost-saving function being applied, we again, we disaggregate the assets that we previously aggregated to see which one should be deployed at each time step of the day. So I know that the legend is very, very small, but on the in blue, we have the maximum energy consumption. The yellow is the EV, so we also have this service where people say when they want to have their EV cars charged and at what level they want to have the car at that point. So according with that, we can also predict when it will be available. Then Green is the domestic hot water, and red is the building heating consumption. Finally, we have the actuation. So I know this is a messy picture, but usually we don't install like this in people's houses, but it was just for representation. Yeah, not perfect. Continuing, basically we have two ways of actuating and also using the flexibility inside the buildings. The first one is the automatic actuation, so we can control HVAC units, air conditioning units, or heat pumps using the switch that were installed in people's houses, but also the fact that we can, in commercial buildings, we have access also to the HVAC system and the SCADA systems, we can control it directly. On the other hand, when we cannot control it directly because the plugs don't allow it, we have the user in the loop actuation. Basically, this what means is that we're gonna send, basically on the typical profile of users, their preferences that they have put in on the platform, we can recommend based on price scheduling and also when, for example, solar energy is more available, what will be the best hour for them to put these assets running. We have the white goods, so washing machines, dryers, and dishwasher that consume quite a lot of energy in fixed periods of time and can more or less be easily scheduled. Then we have EV charging, which also can be more or less changed if you are charging at your home. And we also have one function or a user in loop function that is based on indoor air quality and more specifically CO2 concentrations. We can tell users to open or close their windows so they can increase the comfort inside the room. So going to the results, and apologies for the small legends that we have in the figure. So this is a result of Novo Rumo building, which is one of the residential foster homes that we have in Lisbon. In blue, we have the baseline, so what was the typical schedule. Then on green, we have the upper bound of the flexibility that we have come up with, and the red is the lower bound of the flexibility that we are allowed to use inside this building. In purple or pink, this is the price of energy, and yellow is the aggregated decision that was made up there. So you can see basically the period with most aggregated flexibility is around during the daytime. So when the energy prices are low, so it will be easier to control these systems and also have the best results for the building. The aggregated decision could be much higher than the upper boundary, but in the end, the flexibility that will be deployed, even considering also the lower boundary, should follow the green or the green or the red light. So we're not going to use a lot of flexibility and disturb people's comfort. On the other side, we have the office building in Spain. The flexibility here is more or less concentrated in some periods of time because during the day people will have to be running the HVAC systems, and also there's not much potential to shift loads. But there are still some periods where it's possible, especially during the night and also before the entrance of people in the office buildings, because again we can do some preheating like was previously explained by the two previous presentations. On the Danish pilot, we were controlling mainly the white good appliances, not controlling, but giving user in loop feedback so they can control the appliances. Basically here we have again, here is a bit better, so but red is the energy prices, this dotted line in gray is the baseline consumption, and the blue one is what the project predicted to be the best behavior to achieve. Again, during daytime when the energy prices are lower, we have the best time of the day to use this. And one on the right side, we also have the a prediction what was the baseline. So starting again, here we have different lines. So this is the washing machine. This is time. We know that people can use the washing machine between 9 and 20 o'clock. And we know that the baseline of the users, according to the feedback that we receive from them and also the measure data that we have, they usually put this to work around 13. After running the algorithms, we came up that the best hour to run the washing machine was around 6 o'clock, and thus the users will have very good benefits in the end of the day if they use this user-in-the-loop interaction for all their machines. We did it for washing machines, dryers, and dishwashers, and you can see that usually this is the energy prices. The best hour will be the year because it's cheaper, but we also have to take in consideration that maybe not all the devices can run simultaneously, and that's why they are more or less aligned, but not perfectly aligned with the schedule. We can also see that, for example, the dryer and the dishwasher usually run in early night, when prices are higher, and thus not benefiting the consumers. Finally, I have this confusing figure, but basically here you have 20 lines that represent 20 houses. This is a cumulative. This is cumulative during a month. We have the cost percentage reduction if people used the user-in-the-loop interaction of all those devices that I mentioned before, and also the price that the market have during that period. Basically, the main result, and it's not easy to see, it also confused me a bit, but basically we can reduce on average after 30 days between 20 and 60% of the energy prices that people have in their houses cumulatively. And we can see that also the algorithm tends to that value after some days of understanding also the behavior and the typical users of the typical usage of these vehicles. To conclude, again, the objective of SMART2B was to align with the Smart Readiness Indicator and increase the smartness of the buildings, and we managed to do that. On average, we improved 16.54%. Also, we achieved energy savings of 6.54%. Actually, this was also a surprising because we installed a lot of ACs in people's houses, especially on the foster kids' house, and we expected to have an increase in consumption because before they didn't use much of it, but in the end it resulted in energy savings in all pilots, and especially reducing, in every pilot it was a surprise, but also the value is okay. Regarding cost reductions, if we use the user in the loop, but also the other algorithms to control the equipment that we have, for example, in commercial buildings, we can achieve 18% reduction. We untapped 23.4 to 45 kilowatt hour of flexibility, mainly in residential, but also in commercial buildings. And last one, we have a slight increase in air quality and comfort level, according to surveys that we also did, and that is also a good indicator. So, thank you. And
thank you. Thank you very much. Okay, we are perfectly in time. So now is a section which could be useful for a question and answer session. If you want to discuss with our discussants, and any clarifying needed from the themes of this morning. Come on, don't be shy. That's one. Okay. You need a mic. Thank you, Joao.
Thank you. I have a question for Joao, but
the other Joao.
the SATO project.
Okay.
Yeah. I think he left.
He's not here.
He
okay.
left. Yeah, it's okay.
But you can I think, ask Professor Ferreira, which is SATO coordinator.
SATO has 2 heads. I am computer science. The
Okay.
others are energy and physics people. So
of course. So maybe we will keep 5 minutes with for your question. Any other?
Then maybe I can ask a question for this João.
Please, yeah.
In one of the graphs that you showed in your presentation here, there was one about aggregated flexibility. So that's upward flexibility, power reduction, right? The slide before this one, yes, here the yellow curve. So when you say aggregated decision, is that?
Yeah, I can answer here. Yes.
Sure.
Not exactly. So that's the aggregated flexibility that exists in the bill. It could be upwards or downwards, but we consider, because that's why we have a lower boundary and upper boundary. And basically we consider that every asset that's inside the building, it could be shift or not in terms of the hour of the day. So it also, basically is the total that exists, it could be used upwards or also downwards, it's not specifically here.
Okay, thanks.
Thank you for your question.
Hi. Do you have a measurement about the last presentation about how responsive the users were to the signals that you sent? I mean, in what percentage did they answer to the signal and reduce their consumption or make it up, and in what not?
Yeah, I think you meant here and here. So in the end, I think most of these users, all of them, don't have energy prices that are associated with the energy market. So that doesn't work quite well for them like that. But we send the signals anyway, just to see what they would respond. I don't have the exact numbers of how they shift their consumption, but what this service was not developed by us, but the results that the colleagues transmitted, that was a good response. We will not say it's 100% or even 50%, but having some interaction is already good in a project like this. But I can get the data and share with you. Thank you.
So the other João is back. And, thank you.
It's a one-time fitting process, so we calibrate the model with a charge and discharge of the indoor temperature, and after that we can update this fitting process like winter and summer. They have difference because of the indoor-outdoor resistance will be different, but this is one fit per season, let's say.
What is the length of the data? Because usually in the system identification you need a long data set with rich data.
We have like 1 day with minute data, so.
And that's enough.
Yeah.
The system identification for.
Yeah.
Even variations in external temperature.
Yes.
Any question for Professor Pagliano, which is the only one that hadn't questions yet? A lot of questions for Professor Pagliano could be answered. Please, yeah. Okay. Then there's João, which has another question for Professor Pagliano, for Lorenzo. Okay, please.
Yes, I had a question about, because it was interesting to see that the heat could be turned off for so many days, and there was quite a small difference in temperature. Did you do any qualitative interviews or something with the residents about how did they experience it at all? Because I know it was a mistake when the heat pump was turned off. So did they complain eventually about even a smaller difference in temperature?
I think we discovered the fact afterwards. So it was not planned, and there was no interview planned. The anecdotal report from the manager of the building is that they didn't get much complaints, many people calling, or so, and that's why we discovered that the plant was off only after a few days. Obviously, it's not, we don't have numbers. We didn't interview all the people, and that would be very interesting to have.
We are performing forms anyway, but the results will come later. Yeah. Okay. Any other question? There's Joao. You had question. Oh, okay.
Thank you for making this question.
Okay.
But in the video, the building has appeared on national television just few weeks ago, and there were interviews with some of the
September
occupants.
the 1st, it was like...
and okay, we had, again, anecdotal. Some people who were showing a lot of appreciation for the new situation after the retrofit, obviously, for higher comfort and reduction of the bill, obviously, but obviously the flexibility is a bit more subtle to be asked. Reactions to that. We will have to do tests, and some of the things we have seen presented by the Joaos are on short-term changes. We were exploring what can be done on longer in a longer duration for two reasons: for the safety reasons, because unfortunately you see what's happening in Italy now. So big problems are arising. Safe building is much better than to have, but also because of oscillations we might have in the renewable availability. So you might have 3 days of shining sun and then long time without. So we were exploring the possibility of storing renewable energy for a few days in the thermal mass, and then knowing that, okay, forecast is it will be raining or cover for the next week. We charge the building now that we have the sun, and then so we have photovoltaic and a heat pump. So that's the idea of a longer term to adapt to the variability of the weather.
And about the photovoltaic, it of course saves a lot of surface because you need less.
Obviously all the exercise is much more realistic because we have reduced the energy needs of 80%, so all the size of the surface for the captation is reduced. So in general, reducing demand by a good envelope makes all the rest much easier. More flexibility, lower costs for the plants. So again, probably the cooperation between the envelope and all the controls is what we should look for, because the two are, let's say, really two elements of a couple of that has a lot of synergy.
For a faster energy transition. Okay, thank you very much. Now let's have a coffee, and then we'll go on with techniques of how to do that. And last but not least, the city of Milan, which will give us its impression. Thank you very much, and see you in 10 minutes, okay? Was it like 10 minutes? Enough for a coffee? Yeah, okay.